Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, so the third thing was about genome sequences. I want to give quick 2 examples, then we'll be done for the day. Example, this involves that how long does it take to sequence genome? Because this is sort of an important number. If it took, each one of them took 1 year, then of course we'll be in big trouble. So we want to quickly take a look. And we are saying here that assume that the loading efficiency about 20%. So 20% of the genome sequencer, remember the beads sitting in various places, 20% of them has DNA in it. So that's what the loading efficiency means. So let's see. So you remember the problem we are trying to calculate is 2 things. One is that once you have a DNA, you cut them up in multiple pieces and then you amplify them. So the question we are asking how big it has to be. I said it has to be about 100 to 1,000. We'll see what the exact number is. And second is that once all this reactions takes place, if each reaction has a certain amount of time, let's say 4 seconds, then the entire thing would take about 16 seconds for each base pair. And if you have a certain number to read, 1, 2, 3, 4, 5, 6, and so on and so forth, then you would have to multiply with that many numbers. So let's see how long it takes for genome sequencing. So I said that if it is possible to read it by 20%, and let's say we have 100 million sequences at the same time. So what would be the total? So let's say we have 100 million transistors, right? 100 million transistors. And of them, only 20% sort of can read it. So how many? We have 20 million active sequencers. And if the DNA is 4 billion base pair long, you have to divide by 20 million. So each one of them, the read length in each well would be about 200. Now, if each read takes about 10 seconds, let's say, and we have 4 base pairs that we have to sort of try before we find out exactly which one it is, then it will take 40 seconds. And 40 seconds multiplied by, and there are 200 of them, so total of about 8,000 seconds. That means just a couple of hours. So you can just do it in a couple of hours. And remember, then you have to do it a couple of times so that you can align them and find out exactly the right order. Let's say you want to do them 5 reads. So you can do it in half a day. The entire sequencing that previously had taken 10 years, you can do the whole thing in any given machine. And you can do 1 or 2 every hour, every day in terms of genome sequencing. So it's very, very efficient, as you can see. Actually, the main problem is that even after your read are done, in order to do this computer alignment, that takes much longer. So these days, it's the computation that's the bottleneck, not the reading of the genome itself. All right. And then finally, I'll show you some examples because about the dynamics of genome sequencing using the ion torrent example. So you remember that when we are discussing in the class, in the lecture, that this is the bead and the DNA were decorated around it, and then they were diffusing out. The question we asked that how long does it take for these beads for the proton to come to the sensor surface. And these were sort of the symbols, right? These had sort of the spikes were sort of the signal reaching the sensor surface. So we did a quick calculation. I said numerically, if you have a certain size, and these are experimental data, the symbols and the continuous line, they will match very, very well. But of course, I didn't really solve the problem exactly. It's a 3-dimensional problem. There's this sphere and all sorts of complications. So you can do it numerically. That's not a problem. So what I want to show you here is that you can get the essence that why there is this particular shape, right? A peak and then things go down by solving a much simpler problem. And the much simpler problem has to do with just inject the DNA, the proton at a given point, and then you solve for the diffusion and see how the molecules essentially arrive at the sensor surface. So the solution was already given, and the solution has this particular form. Now, why this? You see, solution has these two components. You have this plus this component. Why are these two components? Very briefly, of course, you could just take the solution and do it. But the way the solution was done, that assume that this is your sensor. And this is the point where the blue is where you inject biomolecules and then they diffuse. But if you say that this doesn't absorb anything, it just biomolecule just go and hit the sensor surface and turn back, then the net flux through this red line will be 0 because nothing is going in. And this is a difficult problem to solve, except that once you realize that you can in fact remove the sensor completely, put an image source on the other side, and then solve the whole thing. Because in the infinite media, the solution is known. This is the solution. Solution is known. So you simply add these two solutions, and therefore from 0 to all positive x, if you add the two solutions, they will always be correct. So this is just a mathematical trick to solve the diffusion equation. But the bottom line is you can see how it works. So this is the concentration of the biomolecule. So you inject something here, and within 0.1 r square over d, some time constant, r is from sensor to the injection point, then you will see that the peak, which was a delta function, has gone down, and there is a small amount of, tiny amount of biomolecules or protons which has reached the sensor surface. As time goes on, these are time snapshots. You see the peak will gradually go down, and some of the molecules which have there'll be more and more molecules reaching on the other side after random walk, and the concentration of particles will go up. And eventually, what will happen that if you wait longer, then the peak will completely go away, the concentration will saturate. If you wait even farther along, the entire, this whole concentration will go down as everything will be leaving through the other side, through the open door sort of. So that is what is being shown. For example, at a later time, 0.5, the whole curve is going down. And as you can see that this magnitude will continue to go down as a function of time. And so you can immediately see that why the curve goes up like this, that because this is when the particles start arriving on the surface, and why it goes down, because eventually everything will leave, because this door is open. So even when you put a pulse, in the beginning, a fraction of them will go to the other side. But after getting reflected, the whole thing will gradually get out. So this explains the shape that we saw in the ion torrent curve, right? And you can do the other extreme also. You can assume that every particle that comes there on the sensor surface is captured by the surface molecules. That is just another extreme. In that case, all you have to do is to make sure that these two things come with a negative sign, so that the concentration in the middle always stay equal to 0. And instead of cosine hyperbolic, therefore now you'll have sine hyperbolic. Again, you can do this whole thing the same, but except the only difference you see in the sub-concentration, that this concentration is always 0, because it is sort of removing from the mobile population. Everything that comes there, like a perfect glue, it is removing all the biomolecules. And so therefore this concentration is always 0. And as the whole peak is gradually going down, large fraction of the biomolecules are getting captured. And of course, a fraction of them are escaping to the other side. And so gradually the peak is going down. And Of course, if you run it for a little bit longer time, 0.2, 0.5 to 5, 0.3, then gradually you will see the pulse will go away. And again, once again, you will see the very similar type of time response. There will be a peak at r square over 60, and gradually it will decay. So in practice, in the ion torrent case, there was the genome sequencer case. It was sort of in between. Molecules were getting reflected, but at the same time, some fraction of it were being bound by the OH bonds. You may remember from the pH sequencers. And so therefore, it has a response which is somewhere in between. So that's it. So in this homework, therefore, we have seen a couple of things. The energetics of the binding is something that you need to go through the table a little carefully. Things would become clear. Space selectivity, again, something that you solve one or two problems carefully, that works out. And this genome sequencer problem, where we integrate everything, is actually very easy. We can take example toy problems, just like the two problems I showed, and you can essentially understand most of the essential features relatively simply. Okay, that's it. Thanks.